Okay, good afternoon. I hope all these empty seats are people sleeping it off rather than people who dropped the course. Okay, so two administrative things. One of them is this coming Monday is a holiday, so your assignments that would be due Monday are due Tuesday at noon instead. I think we have that correct in one place and incorrect in another place on the reader. But anyway, it's due Tuesday. Your midterm 1 grades are in GLOOKUP. A bunch of people have come up to ask me about how this all works. So first of all, if you don't already know this, if you log into your class account and you say GLOOKUP, all one word like that, it'll tell you your grades. And you should do that periodically in case something that you turned in doesn't get graded. After a week or two, you should complain about it. If you do GLOOKUP, you will see two grades, one labeled MT1 and one labeled GMT1. MT1 is your individual midterm score. It's out of 40 points. GMT1 is your group score, which I forget. How many points, Jordy? 9 out of 9 points. Thank you. Okay. When we do grade computations at the end of the semester, we take a weighted sum of MT1 and GMT1. And you can see the weights in GLOOKUP also. And if you add up a perfect MT1 score and a perfect GMT1 score and you multiply by those fractions and you add them up, it still comes out to 40 points. The idea of the weighting is that for those 9 points that you did twice, we count 2/3 individual, 1/3 group. In practice, what that means is your group midterm is likely to pull you up by a point or maybe 2 points. It's not going to make an enormous difference in your grade, but a little teeny one. For purposes of should I drop the course or not, my advice is just look at your individual grade, because that's the best measure of where you are at this moment in the course. So big thank you to the TAs for getting the grading done before the drop deadline. And I think that's it for administrative things. I think I've said everything I have to say about the exam scoring. Okay, today what we're looking at is a scheme interpreter written in Scheme. So just first off, why isn't that a stupid thing to do? Because you can't run it unless you already have a scheme interpreter. And it's going to run slower than the one you already have, so what's the point? And the point, of course, is pedagogic. It's for you to learn what an interpreter looks like. But also it means later in the semester, we can play with variant versions of Scheme. We can say, what if we take Scheme and add this feature to it, or change the way it does that? And we'll see some of that later on in the semester. So it lets you do that. It also makes a point, I'll talk more about this when we get to chapter 4, where the book starts doing interpreters. It makes a point about universality of a programmable computer, that we can write one computer program, namely the interpreter, that can do any computation by taking as data a formal description of the algorithm that you want to use. So the Scheme interpreter takes a Scheme program as part of its input data, and it turns that into whatever result you want. And that's really an amazing thing to be able to do, write universal programs. You guys all grew up with this. I just barely grew up with it. I was born just about the time they were building computers that could do that for the first time. A little later. I missed it by a decade, I guess. All right. Up on the screen is the one screenful version of a Scheme interpreter in Scheme. And we're going to start by going through this. It should really not scare away anybody, I think, because it's very simple and you can see all of it. So up at the top is the read eval print loop. It's just like what you remember from the calculator program. It reads an expression, it calls eval on that expression, and then it prints the result. Okay? And then it loops. So read eval print loop. And then we have eval and apply, the same as the big pieces of the calculator program, except because this is scheme instead of calculator language, it's more complicated. We have things like variables. So in scheme, there are 4 kinds of expressions. And you can sort of divide them up into 2 groups like this. So here's expressions. And there are atomic expressions, and there are lists. Atomic means you don't divide it up further into pieces. You just look at it as one thing. So now there's 2 kinds of each of those. The atomic expressions come in self-evaluating. This we saw before in the calculator program where it was the numbers that were self-evaluating. In scheme, there are a few other self-evaluating things, like number sign T and number sign F are self-evaluating. Strings in double quotation marks are self-evaluating. There are a few other things that we're not really getting into. So they're self-evaluating atomic expressions. And then the thing that's new is that there are symbols which are the names of variables. And those are not self-evaluating. The value of a variable is, whatever its stored value is. But it is atomic. When we see a variable, we're sort of at a base case of the recursion in eval. So we have the variable as just a thing to look up and find out what its value is. And then there are lists. And those come in 2 kinds also. And they are the most usual kind. There's a procedure call, a procedure invocation. Those mean the same thing. So usually when you see stuff in parentheses, it's procedure, argument, 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 and we're calling that procedure with those arguments. And the other thing that's in parentheses is what? Special forms. And what's special about special forms is that they don't follow the rule of applicative order. Namely, we don't have to evaluate all the sub-expressions first. And each special form has its own rules for what it evaluates and when and under what circumstances. So our eval here in tiny scheme, oops, there we go, has a cond with 4 cases. And in the real one, when you look at the code, there'll actually be 5 cases. The last one is else error. But basically here, I'm trying to simplify things as much as possible. So we're dividing things into 4 cases. If the expression is self-evaluating, then we return exp, which is the expression itself. So you call eval on 5, you get 5. Right? Next case, it's a symbol, and we look it up. Okay? In this evaluator, which uses the substitution model of evaluation that you learned in Chapter 1, if eval sees a variable, it has to be a global variable because it is something that was defined with a define form at the scheme prompt. Because anything that's an internal definition or that's a formal parameter of a procedure has been substituted out, right, by the time we call eval. Because remember back from Chapter 1, How do we call a procedure? We substitute actual argument values for the formal parameters in the body of the procedure. That gives us an expression that's just like the body of the procedure, but without any local variables. So the variables that we see mostly, almost entirely, are the names of primitive procedures. You know, you say cons, blah, blah, or you say plus, blah, blah. Those things are not self-evaluating. You know, the value of the word CONS is not the word CONS. It's the list, the pair constructor procedure, right? And the value of plus sign is not plus sign. It's the addition procedure, and so on. So in this evaluator, almost every time we see a variable, it's going to be the name of a primitive. Yes?
I was wondering, why do we need self-evaluating things, and why don't we just say everything's a variable, and some variables have a value which is a variable itself?
Okay, he's saying, why don't we eliminate the category of self-evaluating and just say 5 is a variable whose value happens to be 5? I guess that would make it harder rather than easier because, you know, there are infinitely many numbers, right? And we're not really going to have a table someplace that says the value of 5 is 5. So what you're going to end up doing is making this same distinction inside your variable lookup procedure. And it's more obvious to put it out here, okay? Okay, moving right along. There are 2 cases left. It's a special form. And this is the main thing that makes the real scheme evaluator in Scheme bigger than one screenful, which is that each special form has its own algorithm, its own rules for how it's evaluated. And therefore, each special form has a procedure to evaluate it. So when we look at the real thing in a few minutes, we're going to see things like eval if, eval lambda, you know, those things, right? For all of the special forms that we have, which is not going to be, by the way, all the special forms in Scheme. This is a subset of Scheme that we're interpreting right now. But each special form does its own thing. It takes the expression and does whatever it wants with it. And finally, if it isn't one of those things, then it has to be a procedure call. And on this line, and the line after it, oops, what did I just do? I said meta F. I meant to say control F. What? Okay, I'm confused. Oh, I'm in caps lock. What? Well, right? I'm in insert mode. Is that what you're saying? Oh. But kind of weird. No. All right. Okay. I'm not going to touch it. Okay, so this line right here and the line after it, this expression, are the heart of what we're learning from studying this evaluator today. It's not all. There's a lot of details that we're going to learn, but this is really the most essential piece of it, which is how do we evaluate a procedure call? So how do we evaluate a procedure call? Well, we evaluate all the sub-expressions, including the first one. It might be a lambda expression or something, so you have to evaluate it. And we apply, we use apply to call the procedure, which is the value of the first subexpression, with the argument values that are the values of all the rest of the expressions. Okay? So apply, you'll remember from the calculator program, I hope, apply takes two arguments, a procedure and a list of actual argument values. Well, how we get the procedure is we eval the car of the procedure call, because car of the procedure call, its first element, is the subexpression whose value is the procedure that we want. Right? The subexpression itself is, for example, maybe a symbol like plus sign or cons, or it might be a lambda expression, or it might be the call to some procedure that you wrote whose value is a procedure. But one way or another, the value of that first expression has to be a procedure. And then we take could/exp, which is the list of actual argument expressions, and we evaluate each of those by using map. We say map eval over could/exp. So what kind of recursion is this? Tree recursion, right? Because there's more than one recursive call to eval happening for each call to eval. Right? If we call a procedure with 3 arguments, we're going to do actually 4 recursive calls to eval. 1 for the procedure and 3 for the arguments. Okay? So we do that, and then we're in the world of apply. Remember, in the world of apply, there aren't any expressions. There's just values. So apply doesn't know anything about scheme notation. All it knows about is how to call a procedure. Well, as it turns out, there are 2 kinds of procedures. And they are primitive procedures, the ones that are built in to the interpreter, and procedures you create with lambda, including in the actual scheme, lambdas that are hidden inside a define with parentheses around the name, and lambdas that are hidden inside let expressions. Right? But one way or another, there's a lambda that makes the procedure. So if we come down here, oops. What do we do if it's a primitive procedure? Magic. We do magic. Primitive procedures happen by magic. What that means in a real scheme interpreter is that primitive procedures are little chunks of machine language code, things that have been compiled into the native language of the computer hardware that carry out whatever it is that the primitive is supposed to do. For our purposes, I put it as magic because what that means is we're not interested. We just don't know how primitives work. That's for another day. Okay? The interesting part of apply is what happens if it's a lambda-created procedure. Well, if it's a lambda-created procedure, it comes from a lambda expression which looks like lambda of x, y, z, I don't know, plus x times y, z. Okay? That's a lambda expression. And it has formal parameters, and it has a body. And we have selectors, formals and body, that pull out the formal parameters and the body of a procedure, because when we evaluate this lambda expression, we're going to create an abstract data type procedure. And that abstract data type has formals and body as selectors. And the other thing that we have is actual argument values, and that's in args, which is the second argument to apply. Okay? So, The substitution model of evaluation says substitute the formal parameter, substitute the actual argument values for the formal parameters in the body, and then evaluate the resulting expression. And that's what this says. Substitute here, this thing that takes three arguments, body of proc, formals of proc, and args. You wrote that for homework some time ago, right? Who remembers writing substitute? Yay, good. So those of you who don't remember writing substitute, wake up. Those of you who do remember, you understand how this evaluator works, basically. I'm saying this with my fingers slightly crossed because the substitute that you wrote for homework is not quite adequate to use in this interpreter because of the following special wrinkle. Suppose I say lambda of x plus x lambda x times x3 plus x5. Okay? Let's say I call this with the argument 10. Footnote. This is a really stupid way to write code. First of all, you shouldn't have a variable called x unless you're writing a program that's doing, graphing of functions and you have an x this way and a y that way. Then you can get away with calling something x. But usually you should use meaningful variable names. And second of all, more important, if you have a lambda of x, you don't want to also have another lambda of x inside here. It's only going to confuse you. But let's try to unconfuse you by grabbing the yellow chalk that I see over here. Bad planning for lecturing. So I'm calling this whole three-line lambda expression with 10 as the actual argument. So we're going to substitute 10 for x in the body. What is the body of the lambda? It's this. That's the body. Okay. So I substitute this x with 10. I substitute this x with 10. What about this one and this one? Should I put 10s here? Should I say lambda of 10 times 10, 3? No. I certainly don't want to say lambda of 10. That's just nonsense already. But I don't want to substitute this one either. Because for this inner procedure call, here's its body. And what we're going to substitute into that body is the value of plus 10, 5. So this x is 15. Right? So we do 15 times 3 is 45, plus 10 is 55. That's the value of the expression. And when I did that first substitute into the yellow body, this x was what we call protected from substitution by this x. Okay? So the actual substitute function that we're going to look at in a little bit is a little more complicated than the one that you wrote because of that. Now, having said all that, the next thing I want to say is don't put a lot of effort into learning how substitute works. because in a couple of weeks, we're about to learn that scheme doesn't really work this way. That scheme doesn't really do evaluation by substitution. We're going to learn a more sophisticated thing called the environment model of evaluation, which is how scheme really works. Substitution model, it turns out, is adequate for functional programming, but it's not adequate for some other ways of programming. We'll talk about why that is later. For now, all I want to say is just, take on faith that substitute does the right thing. And don't get caught up in the code of it. But you should understand this line where the cursor is blinking, where we take the body of the procedure, and in that body, we replace each occurrence of a formal parameter with the corresponding actual argument value. Apply gets values. So there's no more expressions here when we're in apply, except for the expression that substitute returns. Okay, that's the expression that's this modified version of the procedure body in which we've substituted out the formal parameters and replaced them with the actual arguments. And we have to eval that expression, and that's what it means to call the procedure. So the line we were looking at before where eval calls apply, and this line right here where apply calls eval. These two things together are the heart of the interpreter. Okay, and they constitute a mutual recursion, and therefore a tree recursion. Now, what is it about scheme expressions that makes tree recursion make sense here? And tree recursion works for hierarchies, right? Two-dimensional hierarchies. We were talking about that this whole week. What's the hierarchy in a scheme expression? Well, scheme expressions can have sub-expressions, right? And those sub-expressions can have sub-expressions, and so on. So it's not surprising that there's a tree recursion involved in doing eval. And the other thing is, expressions can call procedures. Those procedures have bodies which are expressions, and so that also gives rise to mutual and therefore tree recursion. Okay? This is worth some study. It's reprinted in my lecture notes. It's nice because, you can see it all at the same time. There it is. And yet, if you understand this, you really are about 3/4 of the way to understanding how a scheme interpreter works. And if you understand eval and you understand apply, and you know what a REPL is, which is the easy part, then you know how a scheme interpreter works. What you don't know yet, you don't know how the special forms are handled, and you don't know certain things that we're totally leaving out of the discussion. You don't know how the primitives work. So you have no idea, for example, what it means for a computer to do arithmetic yet. That you're just taking on faith, that computers can add up numbers. Yeah? Define is a special form, okay? Because its first argument is not evaluated, right? It evaluates its second argument, which is typically a lambda expression. No, now I lost my train of thought. Oh yeah, the things you don't know. So we're taking arithmetic for granted. You're going to take arithmetic for granted in 61B also. In 61C, you learn how computers do arithmetic. Okay? Because that's a very low-level thing to learn. In our curriculum, we start at high levels of abstraction and work our way down to the nitty-gritty of what the hardware is actually doing. So that's something you're not going to learn until later. Another thing that you'll start getting a glimmer of in 61B and a bigger look at in 61C, but you're not going to totally understand until you take operating systems, 162, is memory allocation in the computer. So when I say cons, to make a new pair, somehow my scheme interpreter has to find someplace in memory to put that pair. How that works is actually pretty complicated, and we are totally taking it for granted. That's a way in which we're cheating by writing scheme in scheme. And another reason, for example, why I'd much rather write scheme in scheme than try to write scheme in some other language, where I would have to make explicit more of these choices. So we're ignoring primitives, we're ignoring memory allocation. We're not ignoring special forms, we just haven't gotten to them yet, but we will. Okay, everybody with me? Okay, here goes. Now, do I have, oops. Nope. All right, here's the Scheme 1 evaluator. Here's the read eval print loop. The crucial part is this line right here that says print of eval1 of read. Eval is called eval1 and apply is called apply1 in this Scheme 1 interpreter. Again, because STK has primitive procedures, eval and apply, that we don't want to clobber. Okay? When you read this code, which you should do, it talks a lot about how this all works. So it says right here the thing that I said about 4 kinds of expressions. It says the value of a self-evaluating thing is the value itself. Then it says something a little interesting. Unlike real scheme, an STK procedure is here considered a constant expression. That's a little weird, because you can't type in a procedure. But one of the ways in which we cheat in this interpreter is we take all the procedures that STK knows about and treat them as our primitives. So STK primitives are Scheme 1 primitives, and also things that you defined in STK are Scheme 1 primitives. And as the comment says, because of the way that plays out, when we look at a symbol that's a global variable, we find the value associated with it. It's a procedure. We end up evaluating the procedure. So we just treat that as self-evaluating. Even though you can't type in a procedure, it's sometimes in a recursive call we're going to want to eval a procedure. So that's that. It's a little bit of a kludge. So in the substitution model, we only see global variables, not local ones. In this evaluator, there is no define, and so the only global symbols are the ones that name primitive procedures. Since that's true, instead of actually building a symbol table where we can walk through looking for a name and find the value associated with it, we just cheat and ask STK for the value of symbols. You'll see that in just a moment. Quote is a special form. If is a special form. In this evaluator, not in the real scheme, but in this evaluator, the value of a lambda expression is the expression itself. So we use lambda expressions as the abstract data type to represent non-primitive procedures. Why is that? Well, what do we need to know from a procedure? We need to know the formal parameters and the body. And those things are in the lambda expression. So I'm just going to take the lambda expression itself and say that's the procedure. Okay? And again, all this stuff I'm going over very quickly because you have access to this file, which will tell you all about it. So here is the real eval1. So a self-evaluating expression, a constant, the value is the expression itself. If the expression is a symbol, don't be confused here, we're not calling eval1 on that symbol. That would be an infinite loop. We're calling STK's eval. So when we get down to sort of the base case of an evaluation, which is something atomic that isn't self-evaluating, we say, okay, STK, what's the value of this? And that value will typically be a primitive procedure. That's the only thing we really use globals for. Quote is a special form. This is what happens, remember, when you type a quotation mark, an apostrophe, into the scheme interpreter, the read procedure that we called up here turns that apostrophe into open paren, quote, blah, 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 close paren. Okay? So that is a special form quote, and we're returning here catter of x. Why catter? Because I typed in quote foo like this. The read procedure turned this into quote foo like this. And the value of this expression should be foo, which is the second element of a list. If we look at this quote expression as data, its car is the word quote, its catter is the word foo, so that's what we want. We return its catter. Catter means second element. What if it's an if expression? Okay. Now I have to convince you that this is not cheating. Namely, we're calling STK's if to evaluate the pieces of this. And we're taking advantage of the way STK's if works, which, let me remind you, it's a special form too. It evaluates the first argument, which is this. It's not catter of x, but it's eval1 of catter of x. So we evaluate the first argument to the if. We get true or false. If we get true, then we're going to eval1 the second argument. If not, we're going to eval1 the third argument. Now, why isn't this cheating? Imagine that for homework, you have to write an interpreter for Java in Scheme. Okay? That would be a little much for homework. Maybe a project. Well, Java has a notation that looks like this. No, it doesn't. If x is equal to 0, do some stuff, else, these are braces, do some other stuff, semicolon. Okay? So that's what if looks like in Java. How is your Java interpreter going to evaluate that? Well, the first thing it's going to do is some sort of parsing work, some grammatical work to extract the interesting pieces of that. The interesting pieces are this stuff in parentheses, which is the expression whose value should be true or false. So you grab that. And you grab this stuff, which is what to do if it's true, and you grab this stuff, which is what to do if it's false. The word else is not interesting. These braces are not interesting. This semicolon is not interesting. So we grab these things out of this syntax, and then what do? You're writing a Java interpreter in Scheme. Well, you have an if, right? You say if Java eval of that first thing, then Java eval the second thing, otherwise Java eval the third thing. And you wouldn't feel like you're cheating, right? You'd feel perfectly okay about using a scheme if as the implementation technique for a Java if. Well, we're doing the same job, except we're writing a scheme interpreter in Scheme. It's not cheating to use STK's conditional mechanism as a way of implementing our conditional mechanism. Just to make that point clearer, we could, if we wanted to, change the syntax of scheme if. Okay? So I'm going to write schemulator, a new language, schemulator. And in the schemulator language, you say, if blah, 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 then blah, 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 else blah, blah, blah. All these things in parentheses. Okay? So now along comes an if expression. We see the first word is if. Okay, it's the if special form. How am I going to implement this? Well, I'm going to say if, now this is STK code, if evaluator of cat_exp, then I want to evaluate this, right? This is the car, the catter, the catator, the cateditor. Right? Otherwise, I want to eval the cateditor, which unfortunately doesn't exist. So I'll say, as a primitive, I mean. So I'll say evaluator of listref exp 0, 1, 2, 3, 4, 5. Okay? So now I've written a piece of code that evaluates something that isn't a scheme expression. In Scheme, you can't say that. If blah, else, then blah, else blah. In Scheme, you have to say if blah, blah, blah. So this code is different from the code up on the screen for eval if because it evaluates a different piece of the expression. Writing schemulator like this feels a little bit less like cheating because I'm using STK's if to evaluate something that is not a scheme if. Okay? It's a little bit more like a Java if. You know, we could even put braces in and, you know, make it more interesting. More like a Java if. Well, if it's not cheating for schemulator, it's not cheating for scheme 1 either. It's really okay to use STK's conditional mechanism as part of the algorithm for implementing scheme 1's conditional mechanism. Okay? Now, what we do have to do is make sure that we use scheme 1 techniques to evaluate each of those pieces when it's time to do so. So that has to be an eval 1 in there and not an STK eval for each of those 3 arguments to the if. Any questions about that? Okay, thumbs. Who's with me? Okay. It's really very frustrating when people don't vote because then I feel like not only are they not with me, but they've given up. So if you don't want to depress me, I'd rather see that than nothing. Okay. There's only one other special form in this little scheme interpreter, and that's lambda. And as I said a little while ago, in this trivial scheme interpreter, the value of a lambda expression is the expression itself, because that's how we're going to represent non-primitive procedures. Yeah?
So in this interpreter, it's the procedure itself, you said, as opposed to...
It's the lambda expression itself.
As opposed to the body?
Well, not as opposed to the body. The body is part of the lambda expression. Okay? We could pick some other. So if I were being really elegant about this, instead of saying exp at the end of that line, it would say make procedure lambda formals of exp, lambda body of exp. And make procedure would return a list of length 3 whose car is the word procedure, whose cater is the formals, and whose cateter is the body. But it so happens that I have almost exactly that, except instead of procedure at the front, it says lambda at the front. So I'm just going to use that. Okay? When we get to the real environment model of evaluation, you will see then that in the real scheme, the result of a lambda expression is something more than just what's in the lambda expression itself. And then there's going to be a difference between lambda expressions, which are input, and procedures, which are kind of output of this evaluation process. Okay, but in our simple evaluator, they're the same. So if it's a list, I really should call list here rather than pair, but pair is theta of 1 and list is theta of n. So I cheated and called pair. If it's a list that isn't a special form, what is it? A procedure call, right? So we're going to call this procedure by calling apply 1. And the arguments here we're doing exactly what I did in that tiny one-screen version. Exactly. It's apply 1 of eval the car, which is the procedure we're calling, and map eval over the cdr, which is turning actual argument expressions into actual argument values. Okay? So by now, this little piece of code right here where the cursor is blinking should seem like an old familiar friend you've known since childhood, namely 20 minutes ago. Okay? Questions so far? Okay, we only have 3 minutes for apply, so let's do that quickly. There's a bunch of comments on apply that you can read at your leisure. Here's the code. And again, the tiny version had 2 branches. Here there's 3 branches. The third is else error. So, oops. Thank you. All right. So right here we call procedure question mark. Notice that this is an STK procedure question mark. Right? It's not procedure 1 question mark. So is this an STK procedure? That's asking the question, is this a scheme 1 primitive? Because let me remind you that every procedure in STK we're taking as primitive. All right? So we get sort of at one blow STK's entire repertoire of primitives plus any procedures you may have defined in STK. Well, if it's a primitive procedure, how do we invoke it? And in Tiny, it said do magic. And here's how we do the magic in our case. We call STK's apply. Right? So if it's an STK procedure, then STK knows how to call it, and we just let STK do that. It's important that by the time we get to apply, there's no more notation, only values. Because STK doesn't know about scheme 1 expressions. It does know about values, because they're the same values. Right? There's procedures and numbers and lists and words and sentences and all those things. And by the time we're at apply, that's what we have. We have values rather than the expressions that produce them. So we can just call STK's apply, and it'll all work. Because args has already been translated from the actual argument expressions to the actual argument values. So we're giving apply the right thing. The second case is this a lambda expression? Because when we saw a lambda expression, we returned, whoops, how did I do that? Sorry. We returned x itself as the value. And so it's a lambda. It's a list that starts with lambda, and then the parameters, and then the body. So now what I do here, why did I get louder all of a sudden? I don't know. Have you been not hearing me all this time? Is that why nobody's hands were up? Anyway, okay. This again is exactly what we saw in the tiny version. We call eval on the result of substituting the actual arguments for the formal parameters in the body. Our version of substitute takes an extra fourth argument, which is given here as an empty list. And what that's going to be is a list of variables that we shouldn't substitute for because we're inside a lambda that's inside a lambda. That funny case that I talked about over there. Don't even think about that. Never mind how substitute works because it's not part of the real scheme. What you should understand from apply 1 is that an STK procedure is a scheme 1 primitive, and that lambda expressions are how we represent scheme 1 non-primitives. Okay? If it's a primitive, then we have STK call it. If it's a lambda-created procedure, we evaluate its body after substitution. Okay? The rest of this code is sort of data abstraction a little bit, and then substitute, which is a big mess. And then at the end of this code, there are some examples of using it because since we don't have define, if we want recursive procedures like factorial, we have to make them using the Y Combinator, which was the answer to the extra for experts about how do you do recursion without define. You don't have to do that necessarily. If you're doing non-recursive things, then you can do it all very straightforwardly. Okay, sorry for running over. See you Wednesday of next week. And you do have lab Tuesday or Wednesday.